In the last video, I introduced you to one of the simpler executor service implementations, the single-threaded executor service. Even with this one service and handling only a single thread, you could see that the job of managing threads is simplified. In general, you get an executor service from one of the static methods on executor's class. You pass it a Lambda expression that represents a task that you want to be run. You'll then call execute on that service, and afterwards you have to call shutdown, otherwise the executor service will continue to stay up and running. Maybe you want to include a call to the await termination method if you have something pending or that needs to wait on the completion of that task. In the last video, I also demonstrated additional functionality you can have by creating your own thread factory rather than relying on the implicit one built into these services. These executor service implementations let you stay focused on tasks that need to be run rather than thread creation and management. This becomes even more apparent when we use an executor service that can handle multiple threads. Let's look at that next. I've got the project from the last video open and I'm looking at the main method. I'll again simply rename the main method, so I'll name it single main here, and then I'll create a new main method using the PSVM shortcut. I'll add a count variable which will represent the number of threads I want to run. This will be called count and I'll initialize it to 3. I'll set up a multi-executor variable using type inference again, and I'll start with the executor's class and then dot, so that IntelliJ will list the methods that are available on this class. I'll scroll down a little bit. What I want you to see from this list is all the methods that end in pool. These all return executor service implementations that manage a pool or a group of threads. I'll scroll up a bit and select the newFix thread pool method. In particular, I want the one that takes 2 arguments. I'll pass count as the first argument and new color thread factory as the second argument. This time though, I won't actually pass a color to this constructor. I'll change my color thread factory to be a bit more flexible and to generate a color thread without having to actually specify a color. I can do this with a private field on this class. This will represent the ordinal value of the last color used for a thread name and text color. I'll call this field color value and assign it a 1 because I don't want to use the default color value at 0, which is the ANSI default. I need a noargs constructor, so I'll get IntelliJ to generate that. Next, I'm going to add some code to the new thread method. I'll set up a local variable for the revised thread name. Now, I only want to do this if thread name is null because I don't want to break my existing code, which uses the single argument constructor to pass a specific thread name value. Name will only be null when the noargs constructor on this class is used. I can use the values on the enum in conjunction with the color value to get a color by its ordinal or numeric value. Here, I'll increment the color value, then check if that number is greater than the number of colors set up in the enum. If it is, I'll set the color value back to 1. This means the code will cycle through all the non-default ANSI colors as new threads are created. Finally, I'll set the name of the thread to this new name variable rather than the thread name. Getting back to my new main method, I can see that my code compiles now. I still need to execute the executor, passing it the task I want it to run, which again is the countdown method on this class. I'll iterate using a traditional for loop and the count variable to determine how many tasks to create. I'll call execute on the multi-executor service using the same method reference I had for the single thread example which I showed you previously. Finally, I can't forget to shut down this executor. And that's that. Let's run this. As usual, I'll just run it a couple of times. I get a variety of statements in colored text in black, blue and white countdowns. With this implementation, I can very easily dial up the number of my threads. I'll set count to 6 here. I'll run it again. That adds the green, purple and cyan threads to the mix. I think you'll agree now that using an executor service in this case was much easier than the alternative. Without this service, I'd have to manually instantiate 3 new thread variables, start each, and write some code to have the main thread wait appropriately if needed. This code is cleaner, easier to read, and scalable, meaning that by changing one number in one statement, I can quickly be using a lot more threads to run tasks. Now, what happens if I pass 3 as the count of the fixed pool, but leave the rest of the code as is? I'll leave the variable count set to 6, and instead of passing count to the new fixed thread pool method, I'll pass the number 3 there. I'll run this code again. In this case, I'm only seeing 3 colors in this output. At first glance, you might think that only 3 different tasks were run and not 6. But let's take a closer look at the output. There actually appears to be 2 sets of black countdown statements, 2 sets of blue countdowns, and 2 of the white also. Did our code fail? No, our code didn't fail at all. This behavior is a feature of this class because only 3 threads were created in this scenario. Remember, it's the thread creation process that gives each thread a unique color. 3 threads were created and pulled. When 6 tasks were submitted, the 3 threads were used to execute the first 3 tasks and then reused to execute the second 3 tasks. This is where the fixed thread pool gets its name. We'll only ever create, at a maximum, the number of threads we specify, regardless of the number of tasks submitted. Let's pause here a minute and just talk about thread pools in general. I think I've stated this before, but I'll say it again. Creating threads, destroying threads, and then creating them again can be expensive. A thread pool mitigates the cost by keeping a set of threads around in a pool for current and future work. Threads, once they complete one task, can then be reassigned to another task without the expense of destroying that thread and creating a new one. A thread pool consists of 3 components. There are worker threads which are available in a pool to execute tasks. They're pre-created and kept alive throughout the lifetime of the application. Submitted tasks are placed in a first-in, first-out queue. Threads pop tasks from the queue and execute them, so they're executed in the order they're submitted. The thread pool manager allocates tasks to threads and ensures proper thread synchronization. Java has 5 variations of the thread pool. You've seen the first in operation, the fixed thread pool. This maintains a fixed number of threads. Threads are reused when the number of tasks exceed the number of threads. The cached thread pool, on the other hand, will grow or shrink in size as the number of tasks changes. The size is managed by the thread pool manager. It's not a one-to-one match to the number of submitted tasks, but you do have to proceed with caution. This kind of pool may create a large number of threads, leading to resource problems. The scheduled thread pool is a special type of cached thread pool with mechanisms for providing a schedule for any submitted tasks. The work stealing pool breaks tasks into subtasks and executes the subtasks in parallel in a divide and conquer way. The fork join pool is a type of work stealing pool that provides the means for describing how to divide and conquer a single large task. It does this by allowing us to control how to fork a task into parallel subtasks and then how to join the subtasks back. In the next few videos, I'll be demonstrating some of these other thread pool executor services in conjunction with some other methods I haven't yet covered available on these services. So I'll see you in that next video.